Okay, so what I'd like to talk about now is part of section 8.3. 8.3 has different applications, and I only want to talk about one application, as that is to calculating the center of mass of a plate, of a flat plate. So here we go. Point 3. Okay, so moments, center of mass. Let's start off with an easy case. Okay, suppose you have, it's well known that if you have a seesaw and you have two persons on it, maybe you have an adult, here's an adult, and you have a kid. The adult is gonna actually, you know, have the balance on her side. But suppose the adult moves over towards the middle and the kid stays on the where the kid is. So the kid is then here and the adult is somewhere over here. Then it balances. And you probably have all tried this when you were kids. So this was discovered, there's a formula discovered by Archimedes. So suppose the distance of the adult is d1 to the fulcrum, and the distance from the kid is d2, and the adult has mass m1, and the kid has mass m2. So then the formula which relates the quantities is that m1 times d1 is equal to m2 times d2. So that's the formula. Now, suppose the fulcrum is located at some point which we'll call x bar, which is the center of mass once the person is moved over, so it's balanced. And suppose the adult is located at point x1, and the kid is located at a point x2 on the x, and this is all on the x-axis. So we're sort of at the x-axis here. Okay, so this would be the point on the x-axis called, this one here would be x1, and this point would be x2 on the x-axis. So the x-axis maybe starts over here. So what does the equation tell us, m1 times d1? Then d1 is x bar minus x1. That's the distance between the 2 points. And d2 is x2 minus x bar, right? So therefore we get this equation. Now we can rewrite this equation in the following way. We can actually take the x bars and put them together. So you get m1 plus m2 times x bar equals m1 x1 plus m2 x2. And then we can solve for x bar, and we get that x bar is m1 x1 plus m2 x2 over m1 plus m2. So we can set m equal to the total mass. That's m1 plus m2, and we get m1 x1 plus m2 x2 over the total mass. So the numerator is a weighted average. And the denominator is like a normalization constant. So this is like how you would, this is very similar to how you would weight an exam, for example, if you have multiple exams. Okay, so that's for two people. In general, you have a question of the following sort. Let me just save the screen. So suppose you have a fulcrum, and you have points. You have a bunch of masses, M1, M2, M3, etc. So about the fulcrum, and M1 has distance D1 to the fulcrum, D2, D3, etc. And you do the same thing we just did before, but we just have more than two people. So then you can think of the x bar as the sum of all the xi's. That xi is the fulcrum is, remember, located at x bar. So it's the sum of mi xi over m, where m is the sum now of the mi. And here maybe I goes from 1 to n. You have n masses. And so this numerator, the numerator of this expression, we'll call it capital M. That's the weighted average. This is the moment. It's called the moment about the fulcrum, about the origin. Okay, so and then the formula is that that m, little m, times x bar is big M. Okay, so I'm going to generalize this now in one more way. Let me erase this picture. Now suppose I have everything superimposed on coordinates. So you have a point x1, y1. You have a point, say, x2, y2, and maybe you have a point x3, y3. So now we have distances to the y-axis. Each one of these points has a distance to the y-axis. So this would be y1. This would be distance y2. This would be distance y3. Oops, that's wrong. It should be x1, x2, x3. Those are the distances. Okay, so now the moment about the y-axis is m sub y. So each one of these points represents a mass, m1, this would be mass m2, etc. So the moment about the y-axis is defined to be the sum of the distances, the weighted averages of the distances to the y-axis. So summation mi xi, I goes from 1 to n. And similarly, the moment about the x-axis is denoted m sub y, capital M sub y, and that summation I goes from 1 to n of mi yi. Okay, so from this we get the equation that x bar is equal to m sub y over the mass m. M, again, recall, is the summation of the mi's, and y bar is m sub x over little m. Okay, so this is this gives you the so-called centroid of the points, or the center of mass of the points. So that's x bar, y bar. Okay, so we're going to generalize this now further. Let me erase. So let's now go to a sort of continuous situation. Suppose I have some plate So R is a plate of density rho. It's a thin plate. So we're thinking of that as in the plane. And so it's a very thin plate. So we want to know what's its center of mass, also called the centroid. Okay, so here's the case we'll consider first. Suppose you have R is given by the region in the plane bounded by a function y equals f of x from x going from a to b, and f of x is greater than or equal to 0. Okay, so what you do is we calculate, we cut this up into strips, as usual, rectangular strips. So let's take one of these rectangles, and we'll compute the centroid on the rectangle. Okay, so maybe this point is denoted xi minus 1, xi, oops. Maybe the left-hand endpoint is xi minus 1. The right-hand endpoint is xi. So now let's say the width of the rectangle is delta x. Now the centroid of a rectangle is located at the center of the rectangle, so that would be the point xi minus 1 plus xi over 2. That would be the halfway point horizontally, and then you have the halfway point vertically, which is 1/2 f of xi. Actually, let's use xi bar, and let's call this point xi bar. So xi bar is this here, xi bar is here. Okay, so that's the centroid of the rectangle. Okay, so now what I would like to do is calculate some things. So what's the area of the rectangle? That's base times height. That's going to be given by delta x times f of xi. And actually, I don't want to calculate the area of the rectangle. I want to calculate the mass of the rectangle. So let me put a row in and call this the mass of the rectangle, because I'm assuming that this is thickness. There's a density, so it would be rho f of xi delta x. And now I want to compute the centroid about the y-axis. So that we saw was m times x bar, and that would be what I just computed, the area, which would be rho of xi times delta x. That would be the mass times, and this would be an xi bar. So that would be that, and so I can rearrange the terms to get rho xi bar, and this should be an f of xi bar, and then there will be a delta x. So that would be m sub y, and then we have similarly m sub x we can compute. M sub x is what? Well, it's going to be given by m times so the centroid of the rectangle about the x-axis can also be computed, and that's going to be given by, what is it given by? It's given by a similar formula. It's going to be the rho f of xi bar delta x times yi bar, and y. What is, actually, that's not correct. I have to put a 1/2 f of xi here, bar. Okay, so then what we're going to do is we're going to sum up over all the rectangles. in the region. And let me just cut to the chase. So if we sum over all rectangles, the following formula comes out. And we're going to take n going to infinity, the number of rectangles going to infinity. So what happens? So then the centroid about the y-axis is the limit as n goes to infinity of the sum over I going n, sum over n, I guess I should write n going to infinity, sum over I going from 1 to n of rho of f of xi bar times times xi bar times delta x. And you stare at this a while, and you see there's just the integral from a to b. The rho comes out. It's just a constant of x times f of x dx. And a similar calculation, which I won't put in, shows that the centroid around the x-axis is rho times the integral from a to b of 1/2 f of x squared dx. Okay, so why did I do this? Because in order to recover, I want to get the centroid of the plate, so we have to take x bar, which we know to be m sub y over m, and this would be the integral of rho, the integral from a to b of x f of x dx. That's the numerator we just calculated. And then we have to divide by rho, integral from a to b, that's the area of f of x dx. The rho's cancel, and we get the integral from a to b of x f of x dx over the area of the under the curve. Okay, so that's x bar. And a similar calculation shows that y bar is given by m sub x over m, and that will give us the integral from a to b. The rows will cancel again, of 1/2 f of x squared dx over the area. So let me summarize. So summary so far is that the centroid under a curve of a region under a curve is given by x bar, which is the integral from a to b of x times f of x dx over the area. Okay, and then these are the coordinates of the centroid, and y bar is the integral from a to b of 1/2 f of x squared dx, and then there's over the area of the curve. Okay, now there's one more case I'd like to consider finally, and this is the most general case we will cover. Suppose now we are considering a plate shaped like a region between two curves, f of x and g of x. So you between a and b. So f of x is greater than or equal to g of x on AB. So in that case, x bar is given by the integral from a to b of x times f of x minus g of x dx over the area. Let's call the area A. And similarly, y bar is given by the integral from a to b of 1/2 f of x squared minus g of x squared dx over the area. Okay, that's the last formula, and that's the most general formula. So I'm going to save the slide, and I'm going to do one example. So let's look at the region. Oops. The region bounded by the two curves y equals x squared and x equals y squared for x between 0 and 1. So what I mean by this is you have y equals x squared, that's the parabola. I'm only caring about x between 0 and 1. And x equals y squared means that x is the square root of, y is the square root of x. So it's this curve here. Okay, so this is the region I mean. We have to first compute the area. So the area is this region here. It's the integral from 0 to 1 of the square root of x minus x squared dx, which is 2/3 x to the 3 halves minus x cubed over 3 from 0 to 1. And this gives me 2/3 minus 1/3 or 1/3. So that's the area. So now I want to compute the numerator of x bar. So I have to compute the integral from 0 to 1 of x times the square root of x minus x squared dx. So it's x times f of x, quantity f of x minus g of x. That's the numerator of x bar. Okay, so what is that? That's going to be the integral from 0 to 1 of x to the 3 halves minus x cubed dx. And that's going to give me 2/5 x to the 5 halves minus x to the 4th over 4 from 0 to 1. And if you plug in the numbers, you should get 3 over 20. Okay, so this is going to be, that means that x bar, let me circle this. Let me do one more calculation. I want to do the calculation for y bar, the numerator of y bar. That would be the integral from 0 to 1 of 1/2. And then I have to take each function, square it, and subtract, and then integrate. So it's x squared that goes in here. Okay, and so this is the integral from 0 to 1 of 1/2 x minus x to the 4th dx, which is 1/2 x squared over 2 minus x to the 5th over 5 from 0 to 1. And 1/2 minus 1/5 times 1/2 gives you, again, 3/20 in this case. You get the same answer because of the symmetry here. Okay, so now we're ready to compute x bar. So let me save the slide, and I'm going to erase the graph because I need some space. So x bar is 3/20 over 1/3, which is the same as 9/20. That comes about because I'm taking this expression we computed here and divided it by the area. And then y bar is actually the same answer in this case. It's 3/20, which 3/20 is this 3/20 divided by 1/3, which is 9/20. So this is the coordinates of the centroid, the center of mass of the region between the two parabolas, and that is all.